Hey guys, today we're going to take a look at linear regression. So, first of all, let's just quickly go through some of these to sort of recap what we've talked about before. So identify the independent and dependent variables. So we want to know which one causes which. Okay. So presumably your heart disease depends on the cholesterol. So your cholesterol is independent. Okay. Heart disease doesn't cause you to have cholesterol levels. It's your cholesterol levels that cause you to have heart disease, or at least that's my vast understanding of how your heart works. Anyway, so hours of basketball practice and free throw success rate. Being good at the free throw line doesn't cause you to play basketball. Probably. I mean, you could argue that if you're good, you might play more, and so you might practice more, but in general, the more you practice, the better you play. Okay? So the independent is the practice. Amount of fertilizer used and the height of the plant. Well, the fertilizer changes the height of the plant, not the other way around. And income level and education. I suppose there is an argument to be made for the inverse, but I think it's fair to say that your education is going to cause you to have a higher income level, probably. Okay? So, each of the type we would expect to see. So, hours of study, examination score. I want you to go through this one yourself and just kind of decide, do you expect it to be strong, moderate, or weak? And do you expect it to be positive or negative? So, take a few minutes yourself and go through those examples. Okay? I do want to recap with you here the meaning of the correlation and coefficient here. So if we have a negative, well, obviously that's negative, okay, because each one is either positive or negative. Obviously a negative one is a negative. So the question is it strong, moderate, or weak? Well, it's strong because the closer to 1 it is, the stronger it is. But in actual fact, because it's right on 1, we will actually say it's not only just strong, we'll actually call that one perfect. Okay, that's a perfect negative correlation. Okay, we can do C next, even though that's not normal. But again, we're negative because it's a negative number. Okay, so as one variable increases, the other decreases. And because it's 0.5, it's right in between 0.33 and 0.67. So that is going to be moderate. Okay, if we jump over to 0, of course, right in the middle. So in actual fact, this one has absolutely no correlation. Okay, no correlation. It is basically it never happens. The only way you would realistically, the only way you're probably going to get a 0 correlation on the nose is if it actually is just a straight horizontal line. Otherwise, it is unlikely you'll get that. But I suppose it's, yeah. Straight vertical line would actually do it too, I suppose. Anyway, 0.2, it's positive, obviously, okay, because it's a positive number. Okay, and it's between 0 and 0.33, so this is pretty weak. Okay, so that'll be weak. So we got weak positive. All right, so here we go. Let's move on to the new stuff. So first of all, what does regression mean? Regression. So this is a statistical technique used to find the relationship between variables for purposes of predicting future values. Okay. So the next one here is interpolation, which is actually not a new term. You should have learned that in grade 9. I'm sure that you all remember it flawlessly. So remember the difference between interpolation and extrapolation. They're both when you're estimating data points. However, interpolation means that you're estimating the points within the data set. So if you have data for X values between 2 and 17, then you're looking at like 15 or 12 or something like that lies between that 2 and that 17. Extrapolation, on the other hand, means you went beyond it and you said, well, based on what happens between 2 and 17, I think at 20 it will look like this. I think at 30 it will look like this. So you've gone beyond the data set. Okay, so I'm going to write that down. Okay, So it is worth mentioning extrapolation. If you find yourself with a linear relationship, it is quite a, there's nothing wrong with that. It's quite a good system. However, when it's not a linear data set, when it's non-linear, it's not necessarily great because sometimes it's just too hard to predict, how fast the data is getting, especially if it's, exponential or quadratic. It's very difficult to extrapolate using that kind of relationship. Okay, but when it's linear, extrapolation works pretty well, or when it seems to be linear anyway. Okay, all right. So let's take a look here at an example. Whoops. So a university would like to construct a mathematical model to predict first-year marks for incoming students based on their achievement in grade 12. A comparison of these marks for a random sample of first-year students is given below. Okay, so there's our data set. So for each student, we have a grade 12 average and a first-year average. Now, it's worth mentioning at this point that this is what makes this unit different from the last unit. Is that we do have, this is what makes it two variable, is that each person has two pieces of data, okay? So each person represents one point where they have something that lies on the X, something that lies on the Y, okay? That's important, especially when we get into the culminating. You're going to need to make sure that you're creating two variable data at times. That's one of the things you have to create, and so you're gonna have to figure out what two pieces of information are you going to gather on each, person or whatever it is, country, whatever it does, depending what you do. Okay. Yeah. So the other thing that we need to decide, first of all, before we even begin to graph this data, is we have to decide which one is the independent and which one is the dependent. And presumably, we would say that your grade 12 mark is going to tell you your first year mark. It's unlikely you're going to care enough to look back the other way. So we would say that the grade 12 mark is the independent, so we will write it as X, and then the first year marks will be your dependent or your Y. Okay? So I'm going to take a minute and I'm going to graph this and then we'll pick it up. Okay, so I've got my graph all drawn there. And yeah, so we can use this to estimate a line of best fit. And again, I mean, it's very difficult to draw a straight line here, so I'll do my best. But so remember, when you draw a line of best fit, you want to get as close to as much of the data as possible. Okay, and if you're eyeballing it like this, you're not going to have something perfect. Especially if you're doing it on a tablet like I am, it's not going to be perfect, and that's okay. It doesn't matter. Okay, so based on that, we look at our line of best fit and we say, well, let's estimate, a student has 82 in grade 12, so what do they have? Well, we go up 82, and it looks like there. So we go over, and it looks like they're going to get about a 72. Okay. And a grade 12 student with a we want the grade 12 marks. They had 65 in first year. So 65 is going right there. And we go down, and it looks like they had about a 75. Okay? It's not perfect, but it's, it's good. That 7 looks like an 8. That's a 7. All right. So, what we can do, though, to make these lines of best fit, we can actually be much, much more accurate. And there is a correct way to find a line of best fit. And what we call it is the least squares fit. Least squares. And this is actually the line that is as close as possible to the points. Okay? And obviously, it is not a great formula. Okay? There it is, but it's y equals ax plus b. To calculate the a, it's all this, which is fun to calculate. We'll do one in a second. And to calculate b, it is just this. So once you've found your a, finding b is not that bad. But, well, finding a is a bit of a chore, as you'll see in a second. So let's just jump over to the next page. And fortunately for you guys, I've done all the work ahead of time. So I'm going to go through, and if you don't believe me, you can try these on your own, but we're going to go through, and I'm just going to say, so this is x, this is y. So the things we need to find, so we need to know what n is, okay? Which, just like before, n is the number of pieces of data, so there's just 10 pieces of data, okay? I am just going to double check that I've used the correct data set. Okay, all right. I have made that mistake before, and I've used the wrong data set, but so we need to add up all the x times the y's, x's times the y's, whatever, you know what I mean. Okay, 64,654. Okay, if we add up all the x's, we'll be left with 844. If we add up all of the y's, it will give us 761. Okay, and finally, the only other things we need the mean of the x's, which is going to be 84.4, because of course you just take the sum and divide it by 10, because there are 10 pieces of data, and the mean of the y is 76.1. So there we go. I think that's, oh no, we do need the sum of x squareds, which is 71,598. And I believe that's it. I think that'll do us. Okay? So, our formula for A. So A is n times the sum of xy minus the sum of the x times the sum of the y. Whole thing divided by n times the sum of x squared minus x, the sum of the x's squared. Okay, so I plug that all in. I get 64,654 minus 844 times 761, all divided by 10 times 71,594, nope, 98, minus 844 squared, which gives us about 1.17. So there's my A. It's nice and easy when I do it. And then to find B, it's going to be 76.1 minus the A value, which was 1.17, times the 84.4, which gives us negative 22.64. There we go. So the perfect equation for the line of best fit here is going to be 1.17x minus 22.65. And there we go. All right. So it's very calculation heavy. They're not necessarily difficult calculations, but it is rather boring, if I'm being honest, because you're just adding up a bunch of numbers. Okay? But anyway, once we use computers, you won't find it that bad. So using the formula, we're going to see, let's see, so if we had 82 in grade 12, so let's say we had y times 1.17 times 82 minus 2, or 22.65. So that would give us 73.3%. Okay, which these are the same numbers we did on the last one. And we'd come up with 74, so we were pretty close. We're only off by a little bit. And if we use it for the other one, so we're subbing in 65 as y, 1.17x minus 22.65, and we solve for x, we would get 74.3%. 0.9, which we had, what did we have? We had, I'm not sure what we had. Let's see, what did we have there? Oh, we had 75. Oh, look at that. We were very close. Hold on, what did we have? We had 72 and 75, and it was supposed to be 73 and 75. Oh, wow. I think we did very well. All right. Okay, so that's it for next time. Until next time, go Sabres.